previous section we called modern climate change, where we looked at changes since the Industrial Revolution. And the new thing compared to the previous time scales like millennial, glacial, deglacial and so on was essentially that we focused a little bit more on forcings. So we looked at the changes in carbon dioxide, methane, nitrous oxide and so on. Also some attention to changing land use, albedo changes and so on. We will now get into future climate change. When we say future, you know that the information has to come from somewhere. The most important thing there is to remember that these are future projections. We briefly mentioned climate prediction, weather prediction, but these are called projections because they are on a much longer time scales for tens of years, some even hundreds of years. And this makes it very imperative that we look at some details of the models themselves, plus the details of how it is that future projections are made, which means what are the assumptions. We don't know in the future how the population will change, how technology will change, how energy production will change and how energy consumption will change. And this means we have to know how the model makes a change once we give it a assumption of, let's say, change in greenhouse gases, because even that we don't know. We have to assume how carbon dioxide and methane will change in the future. And there are two ways to do it. You take the past changes and just continue, or you start to say we will try to define the way they will evolve by doing things that are either to change the way energy is produced and used or the human behavior itself. So if you talk about human behavior, then we have to touch on a little bit of what kind of human mental models work. How do they decide? Given a crisis, what kind of decisions do we make? So we'll briefly look at that. But the most important thing, it turns out to be the concept of climate sensitivity. That means given a change in CO2, what does it mean in terms of temperature change? What does it mean in terms of precipitation change, glacier change and so on? So how do we know what climate sensitivity is? We have to start by looking at what we can infer from past climate changes and then see if the models have similar climate sensitivity. Do they respond the same way for given change in forcings like greenhouse gases? And we also will come to look at how do we decide which way the CO2 will change in the future. So that will come down to two concepts. One is called mitigation, where we try to mitigate our impact on climate change mostly through greenhouse gas emissions, but also through land use change and so on. And the other aspect of it is called adaptation, which means there is some change that is going to happen anyway because we have already emitted certain amount of carbon dioxide since Industrial Revolution. So even if we start emitting carbon dioxide today, some change is going to continue because we know that the residence time of carbon dioxide is many centuries. So how do we adapt to the changes that are inevitable? So it's the concept of avoiding the unmanageable and managing the unavoidable. At least in theory, that's what you want to do. So we'll go through all these concepts and put together a story of what the future projections say. There are many technical details again here. So you as a teacher need to just be familiar with it and realize that some of these details are too technical or too much of assumption involved there that you don't necessarily have to teach in detail in a course, but you need to be aware of what to explain in terms of what future projections mean and how they are supposed to influence policies, energy productions, carbon emissions and so on. So if each country is committing to a global agreement, then each country has to decide how it will reduce its emissions, how it will move around its energy allocation. So essentially going back to what we said before about energy intensity of its GDP, carbon intensity of its energy, and per capita consumption of its citizens and what that amounts to as a total carbon emission and so on. So, let us start with the concept of climate sensitivity. The first thing to note is that there are various estimates, which means that this is not something that is fixed. It depends on how much information you have, and it is not fixed in time, because depending on how much glacier mass there is, how warm the temperature is to begin with, the sensitivity can be and is often different. So, this is a complicated looking figure, but essentially it is showing these range of sensitivities, where these are kind of the outer ranges where the line is dotted. The thin line here is essentially the most likely range, and the box here is the very likely range, and in between this is the likely range and this is the very likely range, and there is a circle in each box that is the most likely range. So, let me not confuse you. The likely range, this is more like in the unlikely range. This is the very likely range in the box, and the circle within the box is the most likely range. So, you can see that this is now split into different periods. Instrumental period is essentially since the Industrial Revolution, where we have been collecting temperatures with thermometers, for example, and precipitation with gauges and so on. And these are the so called probability distribution functions. So, these are the temperature changes that is expected given the forcing changes, whether it is because of volcanoes, solar variability, or greenhouse gases, land use change and so on. And these various estimates give you different probability distribution of temperature change. So, this means here this estimate is saying the maximum probability is around 1 degree centigrade for climate sensitivity. What precisely does that mean? That means it is arbitrarily defined as the amount of temperature change you will get if you double the carbon dioxide concentration and keep it constant at that level. So, I will show a figure next that will make it very clear. So, climate sensitivity is defined as the amount of temperature change you would get if you doubled the carbon dioxide from a given state, let us say from pre-industrial of 280 to 560. You change it with various percentages per year, but typically what is taken is 1% per year, which takes about 70 years to get to double the concentration, and then you keep it constant. Okay? So, these are just different estimates, and the current mean climate estimate is more centered around here. The climate models are essentially in that range, but if you go to the last millennium, when we had the end of the medieval warming and the Little Ice Age, and then the termination of the Little Ice Age, the climate sensitivity was slightly different, and volcanic eruptions have a different climate sensitivity. During the last glacial maximum, the data provide some estimates, and the models seem to be able to mostly reproduce what we can estimate from the data. And here is something that is estimated from millions of years ago, and just like the temperature construction had larger spread as we went back beyond Industrial Revolution, the same will happen to climate sensitivity, because we do not have all the information. For example, if you wanted to estimate climate sensitivity with respect to the last glacial maximum to now, you know what the radiation change was, you know what the temperature change has been, and you can use those to say what the climate sensitivity was or what the climate feedback was. There are slight differences, but let us not worry about the details. So, combining all different estimates, you get estimates probability distribution functions like this. The very likely scenarios and the most likely scenarios are about 3 degrees centigrade for doubling of CO2. You need to be aware of this concept of climate sensitivity, because we need to know what it is, and we need to know what it is in the real world and whether the climate models are similarly sensitive, because if you are projecting into the future, then you are mostly relying on models, and you must have a good sense of whether the model is sensitive to CO2 changes the same way nature would be into the future. And considering it's not stationary in the sense it's not fixed in time, this adds some complications, but we will see that they deal with the models and the projections deal with these uncertainties by creating what are called scenarios. So you provide a large range of projections into the future and say, if you do this, you will end up here with this uncertainty. If you do this, you will end up here with this uncertainty, and so on and so forth. So essentially, climate sensitivity, very important concept. So here is a figure to describe it more properly in terms of changes. So here are the number of years. Here is the temperature change, and here is how the temperature is evolving, and here is the time of doublings of CO2. So that is 70 years for 1% increase per year, and if you want to go to quadruple, it will be 140 years. And the climate sensitivity is done using the calculations with various types of models, but this is a schematic that corresponds to the climate sensitivity that we looked at before, doubling corresponding to about 3 degrees centigrade warming, quadrupling corresponding to about 7 degrees centigrade. The ramping up during the doubling, so as you are increasing by 1% per year, that is called transient climate response. So as you are, like, since industrial revolution, we have been increasing carbon dioxide, which means we are in the transient climate. We are still increasing CO2, so the system is still adjusting. So there is a transient response, but the climate sensitivity is to look at some arbitrary assumption that if we fix the carbon dioxide at that level, what will happen. So the red line here is showing the model simulations coming out of the doubling, and the maximum sensitivity expected is the twice the CO2, what warming is associated with that. So if you fix the CO2 at twice the carbon dioxide of, let's say, the current level or the pre-industrial level, then the warming doesn't stop at the transient climate response, because the CO2 has long residence time. So it will keep on creating additional greenhouse warming till it is removed by either weathering or into the ocean or into vegetation and so on. So that equilibrium temperature will be higher. So that is the additional warming commitment. That means even if you stopped your CO2 emissions at twice the level that you started with, you have already committed to a warming because you have put that much CO2 into the system. So the whole system will equilibrate to a new temperature. That is what your climate sensitivity is. Okay, so there is a similar larger temperature warming and larger additional warming for quadrupling the CO2. Is there an example we can use to explain this? Of course, we looked at it before. I showed this figure several times. We are going back in time to about 500,000 years, and we looked at this from basically this is data from the Vostok ice core in Antarctica, and we said there is a slow decrease in CO2 and the sudden increase, there is a slow decrease in methane and the sudden increase, there is a slow cooling and the sudden warming. And we said when glaciers build, temperatures get colder and colder, so snowfall slows down, ice building slows down, and the cooling is slower. Whereas when you are in a warming phase, ice melting, reduced albedo, increased energy absorption and so on can go very fast, and associated with that you can have very rapid emissions of methane and CO2. So we said glacial deglacial change in CO2 is of the order of 80 to 100 ppm. So in that context, we also mentioned that the scales are different here. During the Industrial Revolution, we have emitted from 280 to now over 400, so more than 120 ppm, which is faster than the deglacial time scales, and we have increased the methane from about 750 to over 1900 So, that is also much faster than anything we have seen. And we mentioned that the temperature is not responding the same fast way as it would in a deglacial, because we are already in a deglacial, and here orbital changes were changing the radiation and temperature first, and then glaciation or deglaciation were responding, and then CO2 and methane were responding and feeding back. They were not the main forcing was typically orbital forcing at these time scales. We looked at other tectonic time scales before, but nonetheless on these time scales we had orbital forcing. So, what is happening here? Essentially this is the slow warming that happens till, so you can see that this keeps on increasing till we reach the committed warming, and you should note that the committed warming is reached earlier when you have 4 times the CO2. So, how rapidly you warm also depends on how much CO2 you put into the system. So, if you put 4 times the current value, you will reach the committed warming much faster, whereas in double CO2 it was a little bit slower. It has not reached even in 500 years, whereas this has already reached in about 400 years. So, this figure is essentially telling you that we are in the transient response and we have not reached the committed warming, which means even if we somehow cap the carbon emissions at this level, let us say 410 ppm, the warming will continue and eventually it will rise and we will reach the climate sensitivity that is corresponding to 420 ppm. This is the important concept of committed warming. That means when we put CO2, we measure ppm, that is the concentration now. But you also have to remember that if the residence time is long, then the carbon is accumulating in the system, it is not going anywhere. So, the accumulated carbon is going to give you the committed warming. That is always something to remember. Another way to look at it, what are the components of the double CO2 warming? You have doubling of the CO2. Let us say we do not worry about the transient response and we have reached equilibrium at double CO2. Some sensitivity will give you direct radiation effect, and we said there is indirect effects through clouds. Clouds will change, their distribution will change, their height will change, their reflectivity will change, their absorption of long wave radiation will change, and so on. So, we right now have quite a bit of uncertainty in exactly what the cloud feedbacks are. Even from observations, it is not very easy to do that, because you have clouds in multiple layers. Satellites can observe maybe the top layer, not always effectively penetrate into the middle and lower layers. Even if you look from the surface using a radiometer towards the sun, you will have the same problem, and so on and so forth. Nonetheless, the progress on modeling the cloud and estimating the cloud effect is improved tremendously since the 90s to now, and it continues to improve even in terms of how we model the cloud. So, certainly in a few years, in the coming years and decades, we will do much better on the cloud albedo, snow albedo, and so on. Snow has a similar problem in terms of knowing the depth versus just the extent. Same for glaciers. Okay. So, there are other feedbacks. For example, water vapor. If you warm, water vapor is going to almost double your feedback, because water vapor is a very strong greenhouse gas. One thing to remember is water vapor is a feedback, in the sense if temperature increases, water vapor increases, if temperature decreases, water vapor decreases. In addition, if you remember the equator to pole temperatures are colder as you go to the pole, so humidity also drops. As you go to higher latitudes, dry climate, it gets very dry. Even here during the winter, humidity is much lower than in the summer. So, that effect is always very nonlinear, but overall water vapor provides a positive feedback, and overall you end up with the sensitivity that we mentioned of 3 degrees centigrade for doubling of the CO2. Okay. That is something to remember. The way to look at the committed warming is essentially to look at the range of temperatures. So, we were here during the pre-industrial 280 ppm and around 15 degrees centigrade. And during the ice house, we were much colder, and during the Cretaceous 100 million years ago, the so-called hot house or the greenhouse, we were way up there with CO2 concentrations of more than 1200 and global mean temperatures more than 5-7 degrees warmer than current. So, there were no glaciers on Antarctica, no sea ice, no Greenland and glacier and so on, forests all the way to the polar circles, etc. And we are in this range somewhere now. So, the sensitivity of the models we will come back to, and the models are not all the same. Some have low sensitivity which are on this trajectory, some models have high sensitivity which are on this trajectory, and essentially we are trying to see the transient response we can measure right now because it is happening now. So, we have warmed about 1 degree centigrade since pre-industrial temperatures. So, that is about 2 degree Fahrenheit. And what is the delayed warming or committed warming? That is kind of the question. So, as we go into the next 50 to 100 years, we will obviously be still changing CO2 unless some enormous game changer comes along and some smart kid invents a way to take out all the carbon from the atmosphere and put it somewhere without it coming back quickly, hide it away on geological time scale or something. We are in a transient climate response. So, those are the things you have to worry about. So, schematically, as we go into the future, we are measuring observed change, and there is some sort of a delayed warming that is expected, and that is going to tell us what the total warming is. So, again, measuring of CO2 is very precise, very accurate. Methane gets a bit harder, but even that is measured very accurately. It is not as well mixed, it does not last as long as CO2, but nonetheless we know the greenhouse forcing pretty well, but the delayed warming into the future, that is where all the projections are. So, that is again the concept of delayed warming. So, here we are, the warming rates are not as fast as here, basically because this is a large ice albedo feedback which we do not have at this time, even though Greenland ice is changing, Arctic ice is changing, Antarctic ice is changing. It is not the same as global deglaciation where the ice extent is very heavy on land, 3 kilometers thick ice sheets coming down to New York and Europe is much heavier than what we have today. So, the delayed warming is going to be on top of this. This is the kind of warming we have been observing. Okay. So, climate sensitivity, committed warming, delayed warming, those are the main concepts that you must explain very well. Detection and attribution I briefly mentioned. Essentially, we have a very well observed forcing signal, and we have a observed signal that is often not as accurate and precise as this, because global mean temperatures are averages of some warming, some cooling, and the coverage of data is not as good. So, the CO2 is well mixed in the sense that as we compared decorrelation of temperature and precipitation and said precipitation is like popcorn, very small scale, temperature is much larger scale, CO2 is even much larger scale, it is hemispheric scale. So, much of the northern hemisphere will be a similar concentration, much of southern hemisphere will be a similar concentration. Mixing across the hemispheres takes about a year, so the hemispheric gradient will be there. So, this is much easier to measure than this, plus this has internal variabilities that also change the dynamics quite a bit. So, the detection was basically measuring this signature, and attribution was to see what are the sources of the warming compared to the variability, where are the volcanoes affecting global temperature, where are things like sunspots affecting global temperature, and of course, CO2 emissions. So, we looked at examples like this where we said the observed variability or trend is shown in the thick black line. The models are reproducing the observed variability fairly well in the red line, but the models tend to somewhat underestimate the internal variability or to be a little bit more precise, even if you start the model simulation at the level of pre-industrial CO2 and using all the temperatures and so on, the model will not exactly match every year to observations. So, 97, 98 in the observations was a strong El Nino, but you can see that models need not produce a strong El Nino at the same time. They will produce it at, this is a La Nina, they will produce it at a different time and so on. So, that is something, but given the radiation forcing, they can produce the global warming very reliably. So, that means you can take the model that is reliable and remove the volcanic forcing, solar forcing and greenhouse forcing, and see if you did not have the forcing, especially the greenhouse forcing, where would the global mean temperatures be. And we said instead of being here, they would be here. So, this is the anthropogenic contribution to observed warming. So, this is what we called attribution. So, detection, attribution, and we looked at the global map as well and said everywhere there is detectable anthropogenic contribution to the warming. So, now how do we then compare to climate sensitivity? So, here it is looking at different periods, 1998 to 2012, 1984 to 1998. So, two different periods and then a longer period. This just re-emphasizes the point I made before, that the natural variability in the models tends to be not in the same phase and may even be underestimated, but obviously there are other biases, we would call them, but you have to be careful with bias because people can misinterpret them. You can call them model uncertainties. So, here is the relative frequency of the times when the different warmings have happened over the different decades, and observations say that during 98 to 2012 the warming was in this range, whereas the models were producing much more warming than in nature. Why is that? Essentially, the global warming pause that we talked about, that is related to probably the eastern Pacific remaining cold. Remember, where the upwelling happens, ocean can take up heat. We said El Niños seem to have changed over that period where the East Pacific remained cooler and the warming mostly happened in the central Pacific and dateline instead of in the eastern Pacific and along the South American coast. Models did not do that very well, so they overestimated the warming. Whereas in the previous period of 84 to 98, the observation said the warming was about 0.3 degree centigrade, more than 0.2 degree centigrade per decade, and few models did that, few models even overestimated, but many models were underestimating the climate sensitivity during that time. Okay, but again, good news is that on longer time scales or anthropogenic time scales or multi-decadal time scales, the models and the observations are in the right range. We can expect this much spread around observations because you can think of it as number of realizations. So, models are different, they have slight difference in the initial conditions. So, the ocean temperatures, atmospheric temperatures, glacier volume, snow volume and vegetation and so on. Those small differences, when you start integrating the model, let us say in the pre-industrial revolution time, the model can produce, if you start here, the models can produce slightly different trajectories of warming based on small differences in initial conditions, whereas Mother Nature used one initial condition that it only knows completely because we do not have all observations all the time, and she follows one trajectory. So, this tells you that if the model is reliable, then Mother Nature could have gone in many trajectories, but she chose one trajectory based on all the initial conditions that she had. So, it is the way to think about it. So, this is why the models, when they do future projections, always make a range of scenarios, and the hope and belief and reliability of the models is that the range of scenarios cover the potential evolution of the Mother Nature, so that you are always in the range of potential solutions as you go into the future. That's very important. So these multiple simulations are called ensembles. They are called ensembles of simulations, which we will come back to. Okay, those are just terminologies again that you should be familiar with. So let's now slowly start getting into how future projections are made. What are the assumptions that go into it? The technical details are, again, they are quite difficult to explain to college students, but as a teacher you should just be aware of the main terminologies, and you should always be able to go back to the IPCC or the skepticalscience.org or Google and look up and be able to explain. That's the main. You don't have to remember everything. You don't necessarily even have to understand all the details, because they are really very difficult even for climate scientists, as I said before. So before the current crop of IPCC projections, which came out in 2014, the projections that started in 1990, and every 7 years they are released. So first assessment report, second, so they are called FAR, SAR, TAR, first, second, third assessment reports. Fourth one was called AR4, and this last one was called AR5, which came out in 2014. As you can guess, the next one will come out in 2021 and will be called AR6, assessment report 6. The exact methodology has changed. Before, we used to assume what trajectories of emission will occur going into the future. So starting in 2000, business as usual means we change nothing and CO2 will increase at a very rapid rate, and we will make many efforts to mitigate and adapt to climate change, which will reduce the emissions. So we will change agricultural methods, irrigation methods, deforestation will be reduced, coal burning will be reduced, renewable energy will be increased, and so on and so forth. And there are some hopeful scenarios where you say we are going to actually flatten out the CO2 emissions at some time in the 2050s and 60s, and so on and so forth. So that is the corresponding. So this is the concentration, and these are the corresponding emissions. So remember, every year we emit certain gigatons of carbon. There is a carbon cycle which takes up CO2 into the ocean, into vegetation, and so on, and gives us the concentration in the atmosphere, which is easily measured. So the emission trajectories would look like this, corresponding to those, and they were called by these various acronyms, which had common themes where they assumed population changes, energy sources, economic development, technologies that will come around like efficient vehicles, efficient airplanes, and so on and so forth. The last set of assessments or projections, and now the future ones, resort to what are called RCPs, or representative concentration pathways. So you can see that they are slightly different. So here again, CO2 emission concentrations are not as straightforward as here. They are slightly different, and each one has a range. And the numbers here, representative concentration pathway 8.5, 6, 4.5, and 2.6, correspond to the radiative forcing that would result from following any of these emission scenarios. So again, here emissions in gigatons carbon have different pathways, and some of them in fact dramatically reduce the emissions into the future. So you know that this assumes some serious efforts on the human side to reduce emissions and even begin to decrease them. Here we are even going into negative ranges. Will there be a time when negative emissions will happen? Let's hope for our children, grandchildren, and great-grandchildren's sake. We never know, right? So these are the various scenarios. So there is a very complicated way in which you can take these emissions and concentrations and run different models to retrieve radiation forcings, and then use those radiation forcings to again run climate models to produce projections of temperature, precipitation, and so on. So remember, these are the main drivers, but then they have to also make assumptions of populations, energy sources, economic development, mitigation and adaptation and so on to get these. So, these are kind of what would drive the policies, the negotiations, the technology and human behavior, if you can believe that. Okay. So, here is the radiative forcing. You can see 8.5 by 2100 goes to there, 6, 4.5 and 2. There are additional details here that provide for. So, when these projections are made under IPCC, there are tens of different groups of modelers from many countries. US, Europe, Africa has no one doing climate projections yet, not at the global scale. China has several. India has just started one that I will come back to. Japan has had some, Australia and so on. So, every group is doing these simulations, which means the protocols that are agreed to are provided to all the modeling groups, and they should strictly follow these protocols to produce the output. Only then you can reasonably compare their projections, their climate sensitivities, etc., etc. That's very important to remember. The kind of assumptions that go in, there are many. There is a huge table of all the observations from the past that are looked at. It's like a massive Excel sheet which is used to produce these future likelihoods of projections. So, here is the primary energy use in exajoules. You can look up, I think that's 10 to the 22, but you can check on me. So, they start with where we were in 2002 in terms of solar, wind, geothermal, hydro, bioenergy, nuclear, natural gas, oil and coal, and each scenario assumes in 2100 what the combination is going to be that gives you. So, the bad news continues. I will show with real examples of how even the major countries which are considered leaders in fighting climate change actually have not gone away from coal yet. Okay? But you can see that oil remains, but we begin to increase things like bioenergy and solar and wind and so on. So, just assumptions made for the future. So, here is the range of scenarios again, and historical emissions are kept in mind, and then future projections of carbon dioxide, methane, N2O and sulfates. Remember, sulfates tend to cool. So, you can see that coal burning reduces, then sulfates cool or clean coal. There are various assumptions again, because these are all future, which means these are not data. These are just what the models assume that will happen or that we want to happen by using some combination of mitigation, adaptation strategies and so on. So, the combined concentration of greenhouse gases obviously and the radiative forcing here, you can see the CO2 concentrations still will be going up quite high. So, when you take all of them together, you convert these into equivalent carbon emissions. So, usually you measure it in ppm, gigatons, or sometimes you see it as gigaton CO2, gigaton carbon or gigaton CO2 equivalent. So, there is using the mass of the molecules and so on, you can always convert to a common unit, which is what is done. Okay? So, there are also other anthropogenic forcings, and there are of course continued emissions from halocarbons in every scenario. So, here is the range of 5 to 50 and 95% confidence of scenarios. Why do we call them scenarios? Because these are just the scenarios we are assuming for the future. So, that is the crux of the projections of the future. There are many details I will keep coming back to. So, we will keep going into projections and keep mentioning the assumptions, but just remember that the most fundamental things you want to explain are the kind of models that go into, that kind of assumptions that go into the RCPs, and the climate sensitivities that we have to keep in mind. So, as I said, the assumptions of greenhouse gases are made, and then you have to make sure that the radiative forcing from those remain at the range you want. Why do we want radiative forcing as opposed to CO2 concentrations? Essentially, we know very well, given the radiative forcing, what the cascades and feedbacks through the climate system are. That's why it's important to take the emissions of all greenhouse gases and also other human activities that we will come back to, convert it to a radiative forcing, including our mitigation and adaptation strategies, and say what is the control we have on the system in terms of radiative forcing. So it's kind of an iteration process where you make the assumptions of the CO2 pathways and you run what are called integrated assessment models, IAMs. What do they do? Unlike the natural system or the climate system we looked at, where we had atmospheric chemistry, carbon cycle, nitrogen, we had sea ice, we had ocean, atmosphere, hydrology, everything, and we produced global climate like El Nino, La Nina, monsoon, PDO, and so on. Assessment models simplify the climate and they look at everything else. They look at the impact of economy, security, food, ecosystems, managed ecosystems, transport, health, and infrastructure, and so on, with energy as the central driver, because that is what is giving you most of the greenhouse gas emissions, and then see how that should produce a net forcing on the climate. Then the climate models are run and then they provide feedback to how food, hydrology, energy, etc. will be affected by the climate change associated with the CO2 emissions you made, and you together produce the greenhouse gases, short-lived species, emissions, land use, and so on, and create the kinds of things that are required to run such models like carbon cycle, chemistry, oceans, climate. For example, to do health, you need atmospheric chemistry or pollution. And then you also look at what are called socio-economic states. So, how many developing countries will be there at any given time? How are they developing? What is their energy source? What is their population growth? And how are they producing their food? Development paths, again, how the energy source is, whether they are importing, burning a lot of coal, and so-called multiple stressors, which means if you have a climate disaster, how will you respond, like a typhoon hits or a cyclone hits, or if you have an earthquake and a tsunami destroys your nuclear plant. So, for example, if India is having heat waves, climate stresses, floods everywhere, and so on, and then some migration stress begins to occur at the borders, then all these together will begin to stress your resources and the priorities will begin to change. So, how do they affect what outcomes the integrated assessment model will give you? So, that is why this has things like security in it, how transportation will be affected, and so on. So, looks complicated, but the main thing you want to remember to teach the kids is that it's not just the climate model. In the previous module, I showed that there are complicated and complex 21st century models that look at ecosystems, biodiversity, energy production, food, water, energy nexus, health impacts, and so on. So, that kind of model has to be always able to be interacting with the natural system, so that the natural human system together decide your future trajectories. Neither one is working in an isolated sense. So, the IOV modeling and research includes these main things, and the climate modeling and research includes these main things, and they have to interact together to produce these scenarios into the future. It is obviously very complicated, but very meticulous worldwide effort, and that's the main thing, that whatever uncertainties there are in the projections, they take many potential scenarios and try to give you a sense of how the system, the earth system, will evolve, including the humans. Remember, we said orbital forcing, solar change, volcanoes are tectonics are the external forcings because they change the radiative balance. But now human beings are also an external forcing because we are taking carbon dioxide that is buried and we are burning it and we are putting into the system in an unnatural way. So we are also an external forcing. So how are we interacting with the earth system and the climate? Because we do something and we react to something when it does something else. So these kind of cascades have to be taken into account. So going from tectonic time scale, orbital time scale, millennial to future projections, the game changes quite a bit because now you are trying to see how we are moving together as a system, and that's something you must convey in the course by knowing as many details as possible but without getting phased by the technical details. So we will get a little bit more into this and address the main projections as we go along. See you next time.